The title of this experiment is Chemical Kinetics, measuring the rate of an SN1/E1 reaction and demonstrating first-order kinetics. As mentioned in the title, we will be measuring the rate at which an SN1 or E1 reaction occurs to confirm if the reaction is in fact first order and to determine the rate constant of said reaction. In a first-order reaction, the rate depends only on the concentration of one reactant. In the case of an SN1 or E1 reaction, that reactant is a tertiary alkyl halide. For this experiment, we'll be deriving the concentration of a reactant at several different time points throughout a reaction and using that information to create a graph that'll help us determine if the reaction is actually first order. Performing kinetics experiments is one tool used to determine if a reaction does in fact follow a specific mechanism. Before we get into the experiment, I would like to explain the mechanism for this specific reaction to you. It involves a tertiary alkyl halide, tert-butyl chloride. Tert-butyl chloride will react in a 50-50 mixture of isopropyl alcohol and water. Because this reaction involves the formation of a carbocation, it undergoes to form both SN1 and E1 products. The products being T-butanol, isobutylene, and hydrochloric acid. The first step of this reaction is the same for both an SN1 and an E1 reaction. The chlorine is attracted to the solvent, so it forms a carbocation. This is the rate determining step of the reaction. The following step for the SN1 reaction is that the solvent acts as a nucleophile and attacks the carbocation. The next step will be an acid-base step to neutralize the product. So we'll lose a hydrogen, leaving our product T-butanol as well as hydrochloric acid in solution. In the E1 reaction, we have the same carbocation. This carbocation has a hydrogen, a beta hydrogen here, and the solvent acts as a base and removes that weak beta hydrogen. This results in the formation of a double bond, as you can see in isobutylene, and again we end up with hydrochloric acid in solution. We expect the kinetics of this reaction to be first ordered because the rate of SN1 and E1 reactions depend only on the concentration of the electrophile, which in this case is our carbocation. For the purpose of the SN1 reaction, the solvent acts as a nucleophile, and for the purpose of the E1 reaction, the solvent acts as a base. We need the solvent to be a weak nucleophile/base for this reaction to proceed as SN1. To go into detail about our experiment, I'll provide you with a brief overview of what we will be doing today. To conduct the experiment, first we will introduce our reactant, T-butyl chloride, to a solvent composed of a 50-50 mixture of isopropyl alcohol, or IPA for short. This results in a chemical reaction that we'd like to determine the kinetics of. To do so, we have to determine the concentration of T-butyl chloride throughout various time points, a process that we will do indirectly by titrating NaOH into the products of our reaction, so that we can manipulate the integrated rate law of a first-order reaction to create a graph that'll show us if our reaction follows first-order kinetics. Part of the reaction is considered the moment that T-butyl chloride is added to an Erlenmeyer flask containing a 50-50 mixture of isopropyl alcohol and water, and the flask is swirled. This flask will be our reaction flask and should be labeled accordingly. This is also the point of the experiment where we will be starting our stopwatch so that we can confirm how long the reaction has been occurring for. At several time points throughout the experiment, we will remove aliquots, or 10 milliliter samples, from our reaction flask using a volumetric pipette and a pipette aid. Aliquoting allows us to work with small samples of our reaction during each time point. After removing the aliquots, we will quench them into flasks containing isopropyl alcohol. Quenching entails dropping the aliquot into a flask containing the isopropyl alcohol to stop the reaction so that any unused reactant will not turn into product. Because isopropyl alcohol is not very polar, it effectively stops the reaction and we can record our time at this point. Having a time point for the moment the aliquot is quenched will allow us to attribute the concentration of the aliquot to a specific time point of the entire reaction. We will quench and subsequently take time points at the 10-minute, 20-minute, 35-minute, 50-minute, 75-minute, 100-minute, and 120-minute segments of our chemical reaction. To take a time point, we'll simply jot down the time from our stopwatch that you quenched each aliquot. Our 120-minute time point will represent when the reaction is over and all the T-butyl chloride has reacted and been converted to products. It has previously been determined for us that this occurs after 2 hours. This 2-hour plus time point is essentially our infinity concentration, since once the reaction is complete, the concentration should be consistent. The data will include an additional time point at the 15-minute mark to compensate for an error that I had made at the 10-minute mark. The goal is to determine the concentration of T-butyl chloride at various time points. For this reaction, the reactants and products occur at a 1-to-1 ratio. For every mole of reactant, we get 1 mole of product, meaning that we can measure the concentration of any of our products to determine the concentration of the reactant at a given time. We don't have a direct way to measure our concentration of T-butyl chloride, but we can use hydrochloric acid's properties to determine its concentration. And because 1 mole of hydrochloric acid produced correlates to 1 mole of T-butyl chloride reacted, we can indirectly calculate the concentration of T-butyl chloride. In solution, hydrochloric acid dissociates into hydrogen plus and chloride minus ions. For the purpose of this experiment, let's keep track of hydrochloric acid as hydrogen ions. The first thing that we know is that the concentration of T-butyl chloride that we start with should equal the concentration of hydrochloric acid and subsequently hydrogen ions when the reaction is complete. That is our infinity concentration. The concentration of our T-butyl chloride at any time point will be equal to the concentration of T-butyl chloride at the start of the reaction minus the concentration of one of the products, in this case hydrogen ions, at that given time point. If we put these 2 points together, we know that our concentration of T-butyl chloride at any given time point is going to be the concentration of hydrogen ions at the infinity time point minus the concentration of our hydrogen ions at a given time point. But how do we determine the concentration of hydrogen ions? To do that, we must titrate with a strong base like sodium hydroxide. So I mentioned that we will titrate sodium hydroxide into hydrochloric acid, but what is titration exactly? Titration is a technique used to determine the concentration of an unknown solution. In this case, we have an acid, hydrochloric acid, which is one of the products of our reaction. The concentration of hydrochloric acid in the aliquot is unknown, and so we'll need to titrate a strong base, sodium hydroxide, to derive that concentration. Sodium hydroxide is our titrant. It will dissociate completely in the presence of hydrochloric acid and form hydroxide ions, which will combine with the hydrogen ions of hydrochloric acid and form water. When equal amounts of hydrogen ions and hydroxide ions combine, the pH will become 7, or neutral. This is known as our equivalence point. What we want to know is, at what time point does this happen? To figure that out, before titrating any NaOH into our aliquot, we need to add phenolphthalein, an indicator that turns a pale pink color when the pH is neutral. As we titrate in our NaOH, we should constantly swirl our flask containing the quenched aliquot. We'll notice that the color will briefly change to a pinkish color. When we're near our equivalency point, that pink color will start to persist. Once the entire solution has turned a pale pink, we know we've found the equivalency point. So, why is this important? The stoichiometric ratio of the titrant, sodium hydroxide, to the product of our reaction, hydrochloric acid, is 1:1. So, once the titration reaches its endpoint, the moles of hydrochloric acid will equal the moles of sodium hydroxide. Because the moles of sodium hydroxide and hydrochloric acid are equal, we can substitute the volume of sodium hydroxide that is added to neutralize our reaction for a concentration of hydrogen ions when we're graphing our integrated rate law. Before we move on, I'd like to point out that a well-formed titration is done in a drop-wise fashion. When the titrant reaches its equivalency point, the solution should turn a pale pink, which will persist for about 30 seconds because of the indicator. If the titrant is over-titrated, you'll end up with a very dark pink color, meaning that you've passed the equivalence point by adding more titrant than was necessary. This will skew our data and should be avoided. As time passes, we should also expect the volume of our titrant required to neutralize the reaction to increase, considering that more products have been formed as the reaction proceeds. If more products are formed, the concentration of the hydrogen ions in the solution will increase, as will the amount of sodium hydroxide that we'll need to titrate to neutralize the hydrogen ions. Now that we've discussed the techniques and our overall goals for this lab, let's gather our materials and get to work. To start our experiment, we should gather all our materials. First, we'll need a 100 milliliter graduated cylinder. We'll also need a 250 milliliter Erlenmeyer flask, which we will label reaction flask. This is where we will carry out our experiment. In addition to a 250 milliliter Erlenmeyer flask, we'll need about 8 125 milliliter Erlenmeyer flasks. In these flasks, we'll perform each of our quenches, and we should label them from 1 to 8 accordingly so that we know which order they have been used in. We'll also need a burette attached to a rig stand to perform our titrations, and a pipette along with a pipette aid so that we can remove our aliquots throughout the experiment. We'll need a small beaker. The beaker will be used to place on top of the burette to prevent any evaporation or CO2 absorption of our NaOH throughout the experiment. Any loss of NaOH could alter our results as far as the volumes of NaOH used. We'll need a watch glass, which we'll place on top of our reaction flask to also avoid any evaporation. And we'll need a long-stemmed funnel to fill our burette with NaOH. You're going to need a small vial of T-butyl chloride, which should be provided to you, as well as a bottle with a 50-50 mixture of isopropyl alcohol with water, and another bottle of pure isopropyl alcohol. To perform our titration, we'll need a bottle of 0.04 molar sodium hydroxide, as well as phenolphthalein indicator. And to measure time points throughout the experiment, we're going to need a stopwatch. And finally, to create our graphs, we'll need a graphing program such as Excel on a laptop or any other electronic device. Once you've gathered all your materials and labeled everything accordingly, you're ready to start the reaction. We will now discuss the procedure in detail. Feel free to pause and rewind at any point to make sure that you have a solid understanding of the steps you will be following. You should also thoroughly read any handouts your professor may have provided before the start of the experiment. At this point, you should have all of your materials gathered and your 250 milliliter and 8 125 milliliter Erlenmeyer flasks labeled. The first thing we are going to do is add our solvent to the 250 milliliter reaction flask. Using your 100 milliliter graduated cylinder, measure out 100 milliliters of your 50-50 mixture of isopropyl alcohol and water. Now, transfer the contents of your graduated cylinder into the 250 milliliter Erlenmeyer flask. You'll need to cover the flask with your watch glass to prevent any solvent from evaporating. You can set this aside while we prepare for the rest of your experiment. So that we're ready to quench our aliquots at each of our time points, we're going to prepare our quench flasks. You'll notice your protocol calls for 7 quench flasks. For the purpose of this video, we'll prepare 8 flasks so that we can have an extra time point in case of any errors while titrating. With a graduated cylinder, measure out 10 milliliters of pure isopropyl alcohol. Then, pour the 10 milliliters into one of your quench flasks. We'll be repeating this process until all 8 quench flasks have 10 milliliters of pure isopropyl alcohol. If you're not confident in your ability to pour the isopropyl alcohol directly from the graduated cylinder, you may choose to use a disposable pipette. Also, make sure that you're using pure isopropyl alcohol for this step, not the 50-50 mixture of isopropyl alcohol and water that we had used when preparing our reaction flasks. Once all of your quench flasks have isopropyl alcohol, we're going to add 5 full drops of phenolphthalein indicator to each flask. You may then choose to cover your flasks until we are ready to use them to avoid any contamination. Next, we will set up our titration. With a clamp, attach your burette to a ring stand like in this drawing. Make sure that your burette is perfectly vertical to ensure you obtain the most accurate results. Now, confirm that your stopcock on the burette is in the closed position. It should be horizontal. Then attach a long-stemmed funnel to the burette. We will be filling our burette with a 0.4 molar solution of sodium hydroxide. Once the sodium hydroxide has been added to the burette, place a small beaker underneath and drain some of the solution to release any air that may be between the tip of the burette. It is also a good idea to measure up to the 0.0 milliliter mark to facilitate your readings during the experiment. At this time, you may also choose to practice opening and closing the stopcock so that you have a good understanding of the flow rate and can release your sodium hydroxide in a drop-wise fashion. It is good practice to cover the burette with a small upside-down beaker. This will minimize evaporation and prevent any CO2 absorption which may hinder your results. Make sure that you have a functioning stopwatch as well as a glass pipette with a pipette aid within your reach, and then call over your professor to confirm that you have an adequate setup. While we wait for the green light from your professor, you should create a table like this to jot down the titration results. It is important to have everything set up before you start your reaction. You will have to move quickly but efficiently to yield the most accurate results. It is helpful to carry this experiment out with a partner, but if you must, you can complete it alone. Once you've received the go-ahead from your professor, open up your stopwatch. Take your vial of T-butyl chloride and add it to your reaction flask. The second that the substrate hits the solvent and you swirl, start your stopwatch. This will be your T0. Your next time point will be at 10 minutes. Remember to return your watch glass to the top of your reaction flask as well. We will now prepare to remove 10 milliliter aliquots from our reaction flask using a 10 milliliter volumetric pipette and a pipette aid. It is important to use a glass volumetric pipette over a graduated cylinder so that you yield more precise and accurate quantities of the reaction. At the 10-minute mark, quench your aliquot by dropping it quickly into your first quench flask. The moment that the aliquot is quenched, record your next time point in minutes. While we wait for our next time point, we will titrate our quench flask with sodium hydroxide. Place the quench flask under the burette tip. Make sure you jot down the burette's initial volume to the first decimal place. In a slow and controlled fashion, add drops of sodium hydroxide into the flask while swirling it. Continue to add sodium hydroxide until the solution turns a very pale pink color, and that color persists for 30 seconds. Make a note that if you take too long to check the color of the solution, it may disappear, but you also need to make sure not to over-titrate the solution or you'll not yield a pale pink color and your results may be inaccurate. If you do over-titrate an aliquot, remember that you have an extra flask and may consider taking an extra reading to make up for it. Be sure to record the final burette volume on your table to the first decimal place. To determine the volume of the sodium hydroxide added to the aliquot, subtract the initial burette volume from your final burette volume and record that data on your table. Repeat the aliquoting and quenching and titrating steps for the remaining time points. Make sure to record your data as you proceed through the experiment. Remember, as time passes, the reaction gears closer to completion, you're going to need greater volumes of sodium hydroxide to neutralize your quench flasks. Be sure to keep an eye on your burette levels because you do not want to run out of sodium hydroxide in the midst of a titration. So that you have a frame of reference, I over-titrated quench flask number 2. As you can tell, the color is significantly darker than the other quench flasks, so subsequently I did take an additional time point reading at 25 minutes. The data that you see on this table is fictitious and is only for demonstration purposes. I will be displaying my actual data momentarily. And please remember that when you record your time points, that should be the time that the flasks are quenched, not once the titration is complete. Once you complete your 2-hour plus time point or your infinity time point, we'll be ready to plot our data and determine if the reaction does in fact follow first order kinetics. I would now like to take some time to discuss the results from my experiment. This table here on the top left refers to my raw data from titrating each of the quenched aliquots. As you can see, time here in minutes refers to the time at which I quenched each of the aliquots into a flask containing pure isopropyl alcohol to stop the reaction. And this volume of sodium hydroxide is the amount of sodium hydroxide that I needed to add to the quenched flask to neutralize them or reach an equivalency point. And it's the difference between my final burette volume and my initial burette volume. The second table on the bottom left represents the data that was used to plot this scatter plot here on the right. And as you can see, I did exclude two of my time points, the 10-minute and the 15-minute time points, and I'll go into further detail as to why momentarily. From my data, you can tell that as time passed, I needed to add progressively greater amounts of sodium hydroxide to reach that equivalence point. And as I mentioned earlier, this is due to more reactants turning into products as the reaction proceeds. This infinity data represented here refers to the amount of sodium hydroxide that I needed to add after the 2-hour mark. And this would be when the reaction was complete, all of the reactant had been turned to products, theoretically. So this table here, my time in minutes, is actually the x values that I used here on the scatter plot and the natural log of the initial concentration divided by the concentration at any given time is this data represented here on the y-axis. Some things that we discussed earlier in the video. Our initial concentration of T-butyl chloride, which would be plugged into that formula that I mentioned earlier, the natural log of our initial concentration divided by our concentration at a given time, would be equal to our concentration of hydrogen ions once the reaction has completed, which would translate to our volume of sodium hydroxide after 2 hours. And then our concentration of T-butyl chloride at any given time would be equal to the volume of sodium hydroxide added after 2 hours minus the volume of sodium hydroxide added at a given time point. This data was used to acquire the values that you see here on the table and as a result on the scatter plot. You may be wondering how exactly plugging in our volumes of sodium hydroxide into this equation, the natural log of the initial concentration divided by the concentration over time, will help us yield information as to whether or not our reaction follows first order kinetics. So this equation is actually derived from the integrated rate law for a first order reaction. In this equation, the concentration at a given time is equal to the initial concentration times Euler's number raised to the negative k, which is a rate constant, times time. Ultimately, what this means is that if a reaction is in fact first order, the concentration of your substrate will decrease exponentially with respect to time since the start of the reaction. So to determine if our reaction is in fact first order, this equation is rearranged through various calculus methods, which I've briefly listed here, and it becomes what we used as our y values on our scatter plot, the natural log of our initial concentration divided by the concentration at a given time is equal to k. K is a rate constant, and that's going to be unique for any reaction, and that's going to be multiplied by time. If you look closely, this new equation is in the format of the equation of a straight line, y equals mx plus b. So in theory, if we plot in our data, and our data approximates to the form of a straight line, then we can say that our reaction followed first order kinetics. In this example, the natural log of our initial concentration divided by our concentration at a given time would represent our y values, and our x values would be time. The slope of the line then would tell us what the rate constant is for our reaction, and we would be able to use that to determine the rate law for this specific reaction. So, as you can see here on my scatter plot, I plotted my results and then I added a linear line. And my points do seem to follow this linear shape, and a good way to determine how close your results are to a straight line is to look at this r-square value. So if an r-square value is greater than 0.9, you can say with some confidence that your results do indicate a first order reaction. And I'd just like to reiterate that, like I mentioned earlier, my x-axis is my time and my y-axis is the natural log of the initial concentration of T-butyl chloride divided by the concentration of T-butyl chloride at a given time. And although we didn't have the concentrations of T-butyl chloride at the given time, we used our volumes of sodium hydroxide to plug into these formulas since those would equate. I would also like to show you here 0.0264, that's going to be the slope of our line, our m value. That's also going to be equal to our rate constant. So we can use this information, our rate constant, to actually determine the rate law for this reaction. And that's going to be listed down here. So the formula for rate law is the rate of a reaction equals to the rate constant times the concentration of the reactant. So our rate constant is 0.0264, and in this case our reactant would be T-butyl chloride. And we would use our concentration, we would refer to that in moles per liter. So for this specific reaction that we carried out, the rate of the reaction is equal to 0.0264 times the concentration of T-butyl chloride. Time to discuss some errors that may have occurred throughout this experiment. I've listed a couple of possible mistakes that can happen while carrying out this experiment, and the points that are underlined are indicative of things that happened while I performed my own experiment. When I went to titrate the first aliquot for my reaction, the solution changed color almost immediately after introducing sodium hydroxide. And after some analysis with Dr. Burdett, I came to the conclusion that I had started with a much smaller quantity of T-butyl chloride than the rest of my classmates. If you look in the protocol, technically we're supposed to start with 1 milliliter of T-butyl chloride. And most students started with about 0.6 milliliters. However, my vial most likely only contains 0.3 milliliters of T-butyl chloride based on the calculations which you can see on the right. Essentially, my products were forming at a much slower rate, and so I needed significantly less volumes of sodium hydroxide to react with hydrochloric acid at each given time point to reach my equivalence point. And as I had mentioned earlier, I did have to exclude 2 of my time points, and this is actually why. Essentially, the 10-minute and the 15-minute time point, those were over-titrated with sodium hydroxide, and so I yielded a very dark pink color from those titrations. And those results, they weren't very indicative of the linear trend from the rest of my data. Again, like I mentioned, starting with that smaller amount of T-butyl chloride contributed to that over-titration. But this is also something that's common throughout the experiment if you're not dropping in your solution drop-wise. Another possible error that can occur is if you use the incorrect solvent when you're quenching. Essentially, if you use your 50-50 mixture of isopropyl alcohol and water instead of pure isopropyl alcohol in your quench flask, then your reaction may not stop and your results would not coordinate with the time point that you have. And forgetting to add an indicator would make it impossible for you to tell once your reaction has reached an equivalence point. Subsequently, you wouldn't know at what volume you neutralized your hydrogen ions with the sodium hydroxide. And also, leaving your reaction flask uncovered could yield issues because some of your solution may evaporate or it can be contaminated. And again, incorrectly recording your time points. If you record your time points once you finish titrating instead of recording the time points, for example, at the moment that you quench your flask, the data would be inaccurate. So the trends in my graph were consistent with that of other students in the class, but like I said, I used a smaller volume of T-butyl chloride. I had a smaller volume of T-butyl chloride and subsequently used a smaller volume of sodium hydroxide compared to my classmates. And in the future, I would just like to mention that it's important to try to avoid these errors. Make sure that you're starting with the correct volumes of your reactants and that nothing has spilled or evaporated in the course of your reaction. You want to make sure that you titrate at a very, very slow speed, drop by drop if possible, and confirm that your color from your indicator persists for at least 30 seconds before you decide that you've reached an equivalence point. Now that our experiment is complete and we've taken some time to discuss the results and any possible errors, I'd like to revert back to our initial goals of the experiment. So our goal was to determine if our reaction did in fact follow first order kinetics, and we also wanted to derive a rate law for our reaction. My results did indicate that the reaction followed first order kinetics. My points fit seemingly well in a linear fashion, and my R-squared value was 0.98. And based on the slope of our line, we were able to determine the rate constant for a reaction and ultimately derive a rate law for this specific reaction. If the data had been incorrect, our graphs would have looked a bit different. If it was a zero order reaction, it may have curved upwards, and if it was a second order reaction, it may have curved downward. And these are visual representations of the three for your reference. So our results followed more of this first order trend that you can see here. If I had the opportunity to repeat this experiment again, I would definitely want to try it in a temperature controlled environment, since fluctuations in temperature would also have an effect on how quickly the reaction proceeded. And instead of titrating and relying on an indicator, I would want to use a pH probe or a pH meter. Using a probe would let me yield a graph with the pH in relation to the volume of sodium hydroxide that I had added to each of my aliquots. And that way, I'd be a little more accurate in determining the equivalence point and subsequently the volume of sodium hydroxide that was added at each time point. This would also help me obtain more accurate data. It may be possible to use a spectrophotometer to determine the concentration of our products instead of titrating our samples. However, those values would be relative to each other and may not be completely applicable. Obviously, in the future, I would also want to try to use the correct amount of reactant when I start this reaction. And I did carry out my experiment alone. I think it would have been helpful to have another person there with me so that the time at which each aliquot was being expelled into the quench flask would have been more precise. And in the future, I would want to take more time points to ensure the accuracy of the results that I had obtained. So to summarize, we did determine that the SN1E1 reaction of T-butyl chloride in a 50-50 mixture of isopropyl alcohol and water did result in a first order kinetics.